Hello, am I audible now? The screen is visible?
Yes, yes, sir.
Yes. Okay. So our course is having advanced power electronics. So what will be will just list the six modules in the course. So first module is PWM rectifiers. So it will be a AC to DC converters or DC to AC. We are already studied the thyristor converter, and we are having some drawbacks of thyristorized rectifiers or converters. These drawbacks we can eliminate with the help of a PWM rectifiers. So basically a PWM rectifier use the MOSFETs or the IGBT devices. These devices are voltage control devices. We can call as a full control devices. So our first module is on PWM rectifiers. You are already studied the inverters, voltage source and current source inverters. What you studied in power electronics, that inverters we can call as a two-level inverter, either three-phase bridge inverter. You have seen a PWM technique or 120 degrees mode of conduction or 180 degrees mode of conduction. What we studied in power electronics, these inverters we are calling as a two-level inverters, and we are having a second module that will be on the multi-level inverters. So we are discuss what is meant by the multi-level inverters in the second module of our syllabus. In power electronics, you have studied DC to DC converters. Another name we can call as choppers. And you are knowing that we have to operate the choppers at high frequency. We have to operate the DC to DC converters at a few megahertz, switching frequencies of megahertz, so that whatever values of L and C required for that will be less. And whenever we are increasing the switching frequency, losses may increase. And here we are having a third topic that will be a resonant converters. We are having a soft switching technique. Turn on and turn off is a soft, and the switching losses will be reduced. So third topic will be on the resonant converters. Then fourth module, we have seen that the solar penetration has increased, and we have to think of some special requirements for inverters required for solar applications. So we are having one module on solar inverters. This is the fourth module will be on the solar inverters. Then you are already studied the cycloconverter, and more advancement in the cycloconverter with the help of full control devices or IGBT MOSFET, that will be a matrix converter. So we are having a fifth module containing the matrix converter, and we are having a Z source inverter. Again, it is a two-level inverter with some benefits that we are going to discuss in the fifth module. And our last module is the active filters. So we'll discuss these active filters in the sixth module. So this is just we are given we are having a six modules in the course, and names of this syllabus you can take it from Moodle, no problem. Then now let us go for what reference books we have to use. So we have listed the already we are knowing one book, that is the BK Bose, Modern Power Electronics and AC Drives. Another book is MH Rasit, Power Electronics, Circuit Devices and Applications, Pearson Education, 3rd edition. Third book is Ned Mohan Robbins and others, that is Power Electronics Converter Application Design, John Wiley and Sons. But we are also require some IEEE transaction papers. So we are more referring on the IEEE transaction papers. So these are reference books and some IEEE papers we are going for this. So now first module is we are calling about a PWM rectifiers, and the first whatever 2 lectures we will be concentrating on the thyristor based converters. Then with that, what are the drawbacks of thyristor converters? Then how these drawbacks can be eliminated with PWM rectifiers, or you can call as converters. In PWM rectifiers, we are having a voltage source PWM rectifier and a current source PWM rectifier. And the control schemes we are having for the these both rectifiers, and we are having the applications of these. Now let us go for already we just take the revision of this, and here we have shown a circuit of a single phase diode bridge. Okay, so our supply voltage, if you see it, is we represented a supply voltage Vs. This is a source inductance we can call as Ls and Rs, where Is is our supply current. A single phase diode bridge consisting of 4 diodes, D1, D2, D3 and D4, and we are having a resistive load of this. So it is a circuit you have studied in 12th as well as you have studied in our power electronics. Now, what will be conduction period of each diode? So, can you just tell me what will be a conduction period? Anyone can unmute and tell me what will be a conduction period of each diode here. What is conduction period of each diode? Anybody can unmute. So, what is the conduction period of diode D1? What is conduction period of diode D1? Loudly.
180 degrees, sir.
So each device here, it is correct. Each device conducts for a period of 180 degrees. And now let us consider positive half cycle of supply. So this is our supply, a positive half cycle of supply. Which devices will be a forward bias here? This is the upper terminal is positive. Let us assume this is positive, this is negative. So we say here a D1 and a D2 will be forward bias. Is it right? In the positive half cycle, devices D1 and D2 will be a forward bias. Sorry for interruption. So here we are discussing about the D1 and D2 positive half cycle, D1 and D2, and we have seen that this is a 180 degrees period where our devices conducting are D1 and a D2. So these two devices will conduct particularly for a positive half cycle, and you have seen that our current will flow. Current will flow from positive half cycle to D1, okay, to the load, from D2, and it will go back to the supply. And this is the output voltage polarity. Upper terminal is positive and the lower is negative. In the negative half cycle, you have seen that the two devices, D3 and D4 will conduct. Okay, and they are also conducting for 180 degrees. Then a current will flow. So now upper, so let us start with our current will flow from D3, goes to this, from this, from a D4, and it will going back to this. So this is our polarity of current. So positive half cycle, current will flow in one direction, negative half cycle. And if you see here, okay, so this will be our source current. Here, let us, before going to that, so our output voltage waveform, everybody knows this positive half cycle D1, D2 conducts. negative half cycle D3, D4 conducts, and this will be our uh, output voltage. And now our load is resistive, so our ID will be the same as VD. So our VDC current, our VDC current will be IDC current will be the similar to a VDC. Okay. And if you see it here on the AC side, same current will flow. Whatever D1 and D2 will flow in the positive. So D1 and D2, this current will flow. The same will flow from supply. So this will be our positive current from the supply. When D3, D4 are conducting, our current will be same wave shape of DC current, but in opposite. Okay, so this will be our source current. So here, what comment you can make for a resistive load? Our supply current is sinusoidal. Is it? Am I audible? Hello.
Yes, sir.
So our supply current is sinusoidal when our load is a resistive load. Is it clear? So the first waveform, if you see it here, it will show the supply voltage, and another is the source current. And we have seen that a supply voltage and source current, they are in phase. First is they are in phase and current is sinusoidal. So that is one conclusion we can draw. Whenever we are having a single phase diode bridge, then source current is a sinusoidal and it will in phase with voltage. So that is an important one conclusion we can draw from our discussion. Now let us how to find out average voltage. Everybody knows. So we want to find out average voltage. We get the area under curve divided by base. Is it right? You can just devise things. So area under curve we are getting. Here our supply voltage peak value we can call as a VM. So our VM is the peak value of supply voltage. We are representing VM as the peak value of supply voltage. So our expression for this wave will be a VM sine theta. Is it right? VM sine theta. And then we can get, so we have to integrate this. So we are having two pulses. So our average expression, voltage expression VDC, okay, it is not necessary to just go over. We can write a VDC will be equal to 2. We are getting pulses in the period of 2 pi, okay, and we can have an integration starting from 0 to pi. Vm sine theta d theta. So Vm sine theta d theta. Okay, I am writing d theta here. Okay, d theta. So once you are having this expression, so area under curve divided by base. So Vm sine theta d theta 0 to pi, it will give area of one pulse. We multiply it by 2, we get a total area divided by 2 pi, we'll get the average voltage. And so you are knowing the average voltage will be a twice Vm by par. So what average voltage we are getting is simplifying this. You are knowing procedure to find out the ripple in the output voltage. So how to find out ripple in the output voltage? This is our wave shape. Is it right? So our wave shape for DC output voltage we are having. This is our output voltage waveform. Is it right? This is our output voltage waveform. How to find out ripple in the output voltage? Anybody? How to find out the ripple in the output voltage? How we find out ripple in the output voltage? What is procedure? Can you recall?
By calculating RMS and average value, sir.
Yes, correct. So we have to calculate the average value. So we have calculated the average value, this. Okay. And RMS value will be a Vm by root 2, particularly for this. Our RMS value will, RMS, how to find out RMS? I think everybody knows it. RMS value will, first you square the waveform. RMS, you start in the reverse direction. So first you square the waveform, whatever given waveform or Vm sine theta, that we have to square it. That is Vm square sine square theta. First you square the waveform, then take the mean of the squared waveform and then take the root. So you go in the reverse way. and we find out our ripple content in the output voltage is around 48.2%. Okay, you can just do this. Then now here we are already listed how to find out the procedure to find out the ripple in the output voltage. So first is you determine the average and RMS values of the waveform. The very first is you determine the average and RMS. Okay, we are. And once you know the average value and RMS value of output voltage waveform, you find out a factor that we can call as a form factor. Form factor is a ratio of form factor is the ratio of RMS value to the average value. So you just once you get the form factor and our percentage ripple, so it will be a square root of form factor square minus 1 into 100. Here 100 is missing. Okay, so percentage we want to find out, multiply it by 100. So percentage ripple we can find out. And here for our diode bridge, just where we are discussed now this case, we are having both values. So what is our RMS value? You find out RMS value Bm by root 2. Here Bm will be the peak amplitude of AC wave. Whatever this particular value is our Vm. Vm is the peak amplitude of AC wave. And for that RMS value is Vm by root 2. Average value, we are just knowing how to find out average value. Area under curve divided by base, that will be twice Vm by pi. So once you know this average and RMS, and now take the RMS value to average value, and it will be a form factor. Now just Vm get cancelled and it is pi divided by 2 root. So form factor will be come out to be a 1.11. And once you know the form factor, and our ripple will be a 48.2%. So this will be our particularly for we revise our single phase diode bridge with R load. And now here, okay, we are going for here our source current, particularly almost sinusoidal. Okay, we are discussing THD, total harmonic distortion. Okay, that slide. Okay, we have to discuss it afterwards. But if you go for this, a total harmonic distortion, we are adding one slide after this. And once you give the source current, this is our source current waveform. If you see, we have taken a simulated with the help of MATLAB, and this is our source current waveform. And whenever current is sinusoidal, our THD, total harmonic content, will be a very, very less. THD of the source current will be less than 1%. Our waveform, if you see it sinusoidal, when waveform is pure sinusoidal, our THD will be almost 0. So here we have seen that any non-sinusoidal waveform, I've forgotten to put a slide here. Okay, tomorrow's lecture will discuss more detail about how to find out the THD. So THD for a sinusoidal current is almost 0. So better way with that, okay, we'll discuss in the tomorrow's lecture. Now let us go for another. Now we can go for again a single phase diode bridge with RC load. Now we change the RC load, change the load from resistance to, we put a capacitor here. If you see it here, we are putting a capacitor here. What is the purpose of capacitor? Anybody can tell? Why we are putting the capacitor here?
To maintain voltage.
Okay, one is to maintain the voltage, and any other word is we want to reduce the ripple in the output voltage. Is it right? So if you observe the waveform across the capacitor, then if you see it here, I'm just showing it here. This will be a waveform. I'm just tracing the waveform across the capacitor or output voltage waveform. It is having a less ripple. When only resistive load is there, our ripple is 48%. Here ripple we can reduce by putting the capacitor. So it is a filter capacitor. So main purpose of the capacitor is we can reduce the ripple in the output voltage. Maybe we are going for 1% or 2%, whereas earlier case the ripple is almost 48%. So we reduce the ripple from 48% to a 2% or 5% with the help of putting the capacitor. Now if you put the capacitor, then now can the diodes will conduct for 180 degrees? Can all these 4 diodes will conduct for 180 degrees? Anybody? So what will happen to a conduction period? Here we have shown it here. Okay, let us assume that. So our AC waveform is there. So this is our AC voltage waveform. I am just making it here, highlighting this. This is our AC input voltage waveform. And this is the capacitor voltage waveform. Already we have shown it here. If you consider the initial period of wave, let us assume that this is supposed to conduct two devices. Which two devices supposed to conduct here? Devices conduction may be our devices D1, and let us assume that devices D2 has to be conduct this particular period. First positive half cycle, we assume that devices D1 and D2 will conduct. We are considering steady state case, and now we have shown the capacitor voltage. If you consider this highlighted portion, we have seen that our instantaneous voltage is less than capacitor voltage. The capacitor voltage, this is a positive, and instantaneous voltage, this particular is positive, but this particular positive voltage or this positive voltage is less than capacitor voltage. Then what will happen to a D1? We have considered the period here. Okay, I am just made a bold portion here, bold particularly this. In that case, what will happen? Our source voltage, supply voltage is less than the capacitor voltage. And obviously, what will happen to our diode D1? What will happen to our diode D1?
Turn off. It will turn off.
It will be a reverse bias, because anode voltage is less than cathode voltage. Here cathode voltage is more. This point will come to the cathode, and capacitor is connected to a cathode, and capacitor voltage is higher. So cathode voltage is higher than the anode voltage. It means that our diode is reverse bias. Similarly, if you see the other period, if you see here a period, this period also, if you see it here, this period, what is happening here? Again, our supply voltage is less than the capacitor voltage, and only a very short duration, our supply voltage will be more than the capacitor voltage. And this particular region, if you see it here, I'll just show with this color. This is the region where our capacitor voltage is less, this particular region, and supply voltage. Only that period, diode D1 and D2 will conduct. So here what we say, a conduction period of diode D1 and D2 are less than 180 degrees. Whereas in case of this particular case, each diode is conducting for a period of 180 degrees, but here these diodes is conducting less, maybe a 40 degrees or maybe a 70 degrees period. And whenever only diode D1 and D2 will conduct, only that period current will be taken from the supply. Current will be taken from the supply. Current will be taken from the supply only when diode D1 and D2 will conduct. And that is why we have seen that a very short duration, if you see it here, this is our current will be taken from the supply. So current taken from the supply is how much duration? Positive half cycle, maybe 70 degrees duration. Current will be taken from 70 degrees duration. Similar situation happens in case of negative half cycle. Negative half cycle, again D3 and D4, they are not conducting for 180 degrees, and they will conduct for a period of, they will conduct just for a period of 70 degrees, and the current, negative side current will be taken, this will be taken like this. So what comment we can make regarding the source current of the diode bridge? What is the your observation? What is the source current of diode bridge when we are having a RC parallel load? Source current is having a positive spike and negative spike. Source current is a positive pulse, you can call it, and a negative pulse. It is not a sinusoidal current. Whereas earlier case, when resistive load, our source current is a sinusoidal. Whereas in case of this, when we are having a RC parallel load, our source current is just the spikes. Our source current is just, we are having a positive spike and negative spike, or positive pulse and the negative pulse. Is it clear? Any doubt? Any question? Hello? Am I audible?
No. Yes, yes. No doubt,
So
sir.
our source current is now not sinusoidal. This source current you can call as a non-sinusoidal. Am I audible? This source current is now a non-sinusoidal. Our source current is something like this: one positive pulse for 70 degrees duration, negative pulse for 70 degrees duration, and other time it will be a zero. And this current you can call it will be a non-sinusoidal current. So when diode bridge is there, bridge is same. If you just change the load and we observe the change in the source current waveform. Okay, we'll discuss this. And now when our load is, we are having the RL load. So we are not the slide here. Okay, when our load is RL, if you are having just the RL load, and now when the load is RL, what will happen to IDC? Let us assume that here we are having a inductance, inductive load, RL load, and we don't have a capacitor. Or we can go for first slide. I will. Whenever here we are having, let us assume that we put a inductor, okay, RL load. Then what change will be there when we put the inductor, large inductor in series with the resistance? Then what will happen? When you put a large inductance, how will be our DC current? Here our DC current is having the same wave shape as that of supply voltage. But when you put a very large value of inductance, then our DC current, IDC, will be a smooth and ripple free. Are you getting? These are the ID, what I am showing it here. Because of the inductor, now our ID will be a smooth and ripple free. Is it clear? If you put a large value of inductance and a resistance, and because of inductor, our current, a DC current, okay, with respect to time, our DC current will become a smooth and ripple free. So our DC current is a smooth and ripple free. And when the DC current is smooth and ripple free, 180 degrees D1 and D2 will conduct. So how is the source current? A constant value of positive constant value of source current when D1, D2 will conduct positive current. And when D3, D4 conducts, our source current will be a constant but in opposite direction. So this will be our nature of source current. So what comment you can make? Whenever we are having RL load, then our source current is the square wave. So this is a combined slide we are showing. We are considering the single phase diode bridge. With R load, what is our current? Source current. R load, our source current is sinusoidal. So this is the first diagram. Whatever we have shown it here is the first diagram, or this first. Okay, you are seeing it here. So whenever we are having a resistive load on single phase diode bridge, our source current is sinusoidal. But what happens when you put a large value of inductance? Our IDC will become a smooth and ripple free. And because of that, here we are seeing that our ID, that will become a smooth and ripple free. This DC current, what we are just, I am showing it here, a DC current highlighter. If you use it, so this is our DC current. This DC current is a smooth and ripple free. And as our DC current is smooth and ripple free, here you are doing positive half cycle. D1 and D2 will conduct for 180 degrees. So this will be a D1, D2 will conduct. And a negative half cycle, D3, D4 will conduct. D3, D4 will conduct. And D1, D2 conducts, current is positive, constant value. So this will be our current, supply current when D1, D2 will conduct. Again, D3, D4 conducts, current will be the constant value but opposite direction at the source side. And so here we have seen it, our source current will be a square wave. So we have considered the three cases. We consider the three cases. A diode bridge with R load, our source current is sinusoidal. A diode bridge with RC parallel load, our source current is having a positive pulse and the negative pulse. It is not the sinusoidal. And when we are having a single phase diode bridge with RL load, then our source current is the a square wave. The source current is the square wave. So this is the what we are. This is our conclusion. So a source current of single phase diode bridge depends upon the load on the converter. Depends upon the load on the converter. Is it clear? Any question on this? What point I want to trace is a source current of single phase diode bridge depends upon the type of load on the rectifier. If rectifier is having R load, our source current will be a sinusoidal. If we are having a spikes, particularly when load is RC parallel, we are having a spikes, this type of current will appear here. If you see it here, this will be a waveform we have taken. And whenever source current, when a load resistance Cauchy square wave waveform we can obtain when we are having a RL load. So any question, any doubt?
No, sir.
So is it clear?
Yes, sir.
Yes. Okay. The source current will depend upon type of load on the single phase diode bridge rectifier. Now let us. We want to go for. I'll just change. Okay. Otherwise, okay. Next time we'll do that. Making this harmonics analysis we'll do next time. So we'll go for now the particularly or better way. Okay. I'll just change the just the 1 minute. So I'll just go for that slides. So let us now we can concentrate. Is it slide is visible? Hello?
Yes, sir.
Yes. Okay. So this will be we can talk about the harmonics when current is non-sinusoidal. Let us you see the yellow waveform. Okay, yellow waveform. This will be somewhat square wave current we can say. So this is a non-sinusoidal current, yellow waveform. You see it will be a non-sinusoidal current, and this non-sinusoidal current can be decomposed into a sinusoids, And this yellow current we are having decomposed into a fundamental. If you see, the fundamental will be our red. This is having same frequency as that of our non-sinusoidal current. So yellow current is the non-sinusoidal current, you can call it. Then third harmonic is having a frequency 3 times that of fundamental. So white waveform, you will see the third harmonic. Okay. Then blue waveform is fifth harmonic and the seventh harmonic. So we can say here, when non-sinusoidal waveform is there, non-sinusoidal waveform can be resolved into a number of sinusoids, composition of number of sinusoids. The sinusoid which is having same frequency of that of non-sinusoidal current, that is called as fundamental. And with respect to that, we are having a, when frequency is 3 times, fifth times, then we get third harmonic, fifth harmonic, and the seventh harmonics. And so here our harmonics are a voltage or current that operates at a frequency that is an integer multiple of fundamental frequency. Our fundamental frequency is 50 Hz. Then the second harmonics is of 100 Hz. 100 Hz signal is present, then it is second order harmonics. 150 Hz is there, then it will be third harmonics. 350 Hz plus seventh harmonic. Now relationship between RMS currents. So here we are having a RMS current. You are knowing square mean root RMS. Okay, so you are already studied in first year definition of RMS current. Okay, based on the heating effect, you are already studied the definition of RMS current. So the RMS current. So here we are written it. This is the RMS current. So this is our RMS current. Total RMS current you can call it. And this RMS current square will be a fundamental current RMS square. This is a fundamental RMS value of fundamental current plus RMS value of second harmonic current square plus RMS value of third harmonic current square, RMS value of fourth, fifth, and so on. So the relationship between RMS current and the fundamental and harmonics will be given by this expression. Is it okay? Is it clear? This is a fundamental expression. So RMS current will be equal to I1 RMS square plus I2 RMS square plus I3 RMS square plus I4 RMS square plus I5th RMS square, and so on. And now this from second onwards, this we can call as a harmonic RMS current. This whatever second, third, fourth, up to whatever may be maximum we are having, that we can add together, and this together adding we can call as a IH RMS square. So now we are having a relationship between three currents: RMS current, then fundamental component of RMS current, and the harmonic RMS current. Is it clear now? We are having a relationship between three currents. We are having a relationship between three currents. What are these three currents? One is the RMS current, what we can calculate, square mean root RMS value, that is RMS current square will be equal to fundamental component of RMS square current. So I1 RMS square plus IH RMS square. So RMS current will be a fundamental RMS current square will be equal to fundamental RMS current square plus the harmonic RMS current square. So this is the relationship we have given it here. So this will be a relationship, and the harmonic current we have seen that it will be a total harmonic current will be a except fundamental, all other harmonics we add together to get the total harmonic current. So IH RMS square, that is a harmonic RMS value of harmonic current square, total harmonic RMS current will be a summation of the second harmonic current square, third harmonic current square, fourth harmonic, fifth harmonic, and this. Now we want to find out the THD. We want to find out the total harmonic distortion. We want to find out the total harmonic distortion. So for given waveform, we can find out these two values. IRMS, just we have find out IRMS, and I1 RMS we find out. For any waveform, we find out two values, IRMS and RMS value of fundamental current. And once you know it, IRMS and I1 RMS, you find out from this expression, you find out IHRMS. Okay. So once IRMS and the I1 RMS is known, for any given waveform, we find out these two values. And from these two values, we find out using this expression. I'll just use the highlighter. Using this expression, we can find out, we are knowing the IRMS, we are knowing the I1 RMS, and from that we can find out the harmonic RMS value of harmonic current. And once you know it, the THD will be given as a ratio of harmonic current RMS value to the fundamental RMS current value. So IHRMS to the I1 RMS, that ratio we can call as the total harmonic distortion. So is it clear? This will be our harmonics, and how to find out the THD, what is mean by the total harmonic distortion. Any doubts? What is the formula for THD? Is it clear?
Yes, sir.
When current is non-sinusoidal or any waveform is non-sinusoidal, it will be resolved into number of sinusoids. Only first we can call as fundamental, others will be the harmonics. For the given waveform, we find out these two values, IRMS square and I1 RMS. And once IRMS square and I1 RMS square is known, we find out the IHRMS square. And once you get that, so THD will be IHRMS to I1 RMS into 100. Now we can apply this procedure to a square waveform. So let us go for the square waveform. So everybody knows this will be a square waveform. Square waveform is having a rich in harmonics. Square waveform is rich in harmonics. And so here, so this is our waveform. Particularly for this waveform, we are going for RMS. We want to find out THD of this square waveform. So we can use, we are going for a very simple method. You can use another method also. These are plus IDC, you can call as the plus IDC and minus IDC. So what is RMS value for this? Plus IDC or plus I and minus I, that will be here, or plus IDC and minus IDC. A square waveform is there. For that, what is the RMS value? Anybody can compute? Square mean root. For this particularly a square wave, we have shown it here. Okay, we are having a peak positive is plus IDC, peak negative is minus IDC, a square wave waveform. For that square waveform, what is the RMS value where peak value is plus IDC or minus IDC?
IDC.
So it will be IDC, is it right? Square mean root. So same is very easily you can get RMS value for the square waveform is same as its peak value. So let us, we find out this value we can call as IRMS. So we find out the IRMS value. Now here we have seen that if you just shift to origin at the center of this, okay, particularly this, so 0 we can just shift here. Okay, you can just see it here. We have shifted the 0 at this, and by considering, then it will have a quarter wave symmetry. If we just shift this, we are having now a quarter wave symmetry. Okay, and once we are having a quarter wave symmetry, there is a well-known expression available that will get the peak amplitude of nth harmonic. A very generalized expression, very simple expression. What is the peak amplitude of nth harmonic? That will be given by an. An will be a peak amplitude of nth harmonic. An will be a peak amplitude of nth harmonic, and it will go to 8 by 2 pi. And here we have to just integrate the period only quarter cycle. So here we have taken the limits will be 0 to pi by 2. We have changed it at the center, we are 0 and pi by 2. So quarter wave, so we are having 8 by 2 pi, 0 to pi by 2. F theta is function. What is here f theta? F theta is IDC only. Here, right? Is it right? Particularly for this case, our f theta will be equal to IDC value. It is constant. From 0 to pi by 2, this particular quarter wave, our current is constant. So I will write it here. F theta will be just the constant value equal to IDC. And cos n theta d theta. You just find out this. And from that, you will get the expression for an. And put n equal to 1. Then you will get the I1. Put n equal to 1. If you put after completing this sine cos n theta, we get a sin n theta upon n, and put n equal to 1. If you put n equal to 1, you will get a peak amplitude of fundamental. Okay, how to get the? We have to just integrate this equation to get expression for an. And once you know the an, you put n equal to 1, you will get the peak amplitude of fundamental. That we can call as I1. And then from that you find out, we get an from this peak value, it will be divided by root 2, you will get the RMS value of fundamental. This expression an will give the peak amplitude of nth harmonic. Put n equal to 1, it will give the A1, it will be a peak amplitude of fundamental. You divide by root 2, so you will get the I1. So you get the RMS value of fundamental, you get the total RMS value. And once you know the total RMS and the RMS value of fundamental, from this you can find out IH. And once you know the IH, you can find out the THD. So for very simple waveforms, for a square waveform, how we find out the THD? Is it clear? Any question? How to find out THD? You have to remember this expression. 8 by 2 pi, 0 to pi by 2, f theta cos n theta d theta. Okay, that will be for a particularly for a quarter wave symmetry. All our waveforms are having a quarter wave symmetry. So it is a very simple method to find out this, particularly the harmonic content. We can find out any amplitude of any harmonic we can find out. So any question?
No, sir.
Any doubt? Yes.
No, sir, no doubt.
Is it clear how? Now we can get what should be the THD of square waveform. Can you just add 2 minutes time and to just find out what should be the value of THD for the square waveform? Let us assume that plus IDC is there. Okay, same waveform, whatever you know, what should be the THD, what should be fundamental. So what should be the THD you can find out. So we can just quickly go through this. So this is again the same waveform we are getting this. This will be a square waveform. We are integrating only from 0 to pi by 2. And you are knowing RMS value will be equal to IDC. Just you find out. Okay, RMS value, square mean root. Square mean root, it will be equal to IDC. And now put here, whatever this our expression for AN. Whatever expression for AN, put f theta will be equal to IDC, integrate it. So it is 8 by 2 pi, 0 to pi by 2 IDC cos n theta d theta. Okay, so here IDC is constant. Okay, IDC you take out this, then cos n theta will be sin n theta divided by n, and then we can just put the limits. So our AN will be a 4 n pi IDC, 4 by n pi IDC sine of n pi by 2. This is our, okay, simple, you can derive it. And now A1, that is a peak amplitude of fundamental. that will be 4 IDC by pi. Putting n equal to 1 and peak amplitude you are getting 4 IDC by pi. So 4 IDC by pi, sine of pi by 2 is 1. So we get a peak amplitude is 4 IDC by pi. And divide it by root 2, you will get the RMS value of fundamental component. RMS value of fundamental component. That is a 2 root 2 by pi IDC. And once you know this, RMS value is known, I1 RMS is known, you find out IH. IH will be, if we just put this, I RMS square will be I1 RMS square plus IH RMS square. And from that, you will get the IH will be IDC, a square root of 1 minus 8 pi square, just putting the value. And then put the IH by I1, will get a 0.48, or our THD, you can call it how much now? THD multiplied by 100, total percentage harmonic. So particularly square wave contains a 48% THD. Is it clear? What I want to say is square waveform contains the 48% THD. So how to compute the THD? And this is what we are having a harmonic spectrum. Particularly this is a square waveform, okay, for a diode bridge single phase RL load. And then we are having, if you here we are generalized expression we obtain, put n equal to 2. What will happen if put n equal to 2? Sine 180 will be 0. So in the square wave you are knowing all even harmonics are absent and only odd harmonics are present. So put n equal to 3, you will get the peak amplitude of, in this expression. In this expression, if you put n equal to 3, you will get a peak amplitude of third harmonic. Put n equal to 5, you get the fifth harmonic. N equal to 7, you get the seventh harmonic. And this is the harmonic spectrum. Third harmonic is 1/3 of fundamental. Fifth harmonic is 1/5 of fundamental. Seventh harmonic is 1/7 of water fundamental. So this will be a what is the value of each harmonic current or voltage, and that is what we can call as the harmonic spectrum. So we have shown up to a 13th harmonic, and as our harmonic number increases, particularly amplitude will go on decreasing. So this is all about our today. We discuss about the single phase diode bridge, and our very important conclusion is a source current of diode bridge depends upon type of load on the single phase diode bridge. R load, source current is sinusoidal. RL load, highly inductive load, our source current is the square wave. And for RC parallel load, our source current is having a positive pulse and the negative pulse. And for this particular waveform, source current waveform, we can find out the total harmonic distortion. What should the ideal value we expect for THD? What should be the ideal value of THD we expect?
0.
0. We want the THD should be 0. So our supply is sinusoidal. So any load, it should draw the sinusoidal current. If it is taking a non-sinusoidal current, then it will be, we are having so many drawbacks of that we are going to discuss. So our interest is any load from the supply, it should take only a sinusoidal current. That is the ideal case, but it is not happening in case of diode bridge with RL load, single phase diode bridge RL load, it takes a square wave current. Or we can say that takes a square wave current means it injects the harmonics into the supply. It injects the harmonics into the supply. It pollutes the supply lines. That is a drawback of our diode bridge rectifier. Is it clear? We are calling these rectifiers as the nonlinear load, and they are not taking a sinusoidal current from the supply, and they take a square wave current. It means they inject the harmonics into the supply. So any questions? Hello?
No, sir. No questions.
No question. Is it okay?
Yes, sir.
Any doubts, any improvement you suggest? Hello. What is today's attendance is, I think, how many? 24.
Actually,
Hello.
sir, yeah, so some students have interviews right now,
Okay,
so
okay, okay, fine, fine.
that's
So we'll share this, okay, a recording, so no problem. Hmm? Okay, fine. So you can ask the question, that is very, very important. Is it right? Okay. So we'll meet tomorrow, same time, tomorrow at 10:15. Is it okay?
okay, sir.
Okay, thank you then. Thank you.